All right, everybody, let's go through day 3 of the immune system. Today we're going to talk about our third line of defense. And this third line of defense is the very specific immunity. This is designed to specifically fight off individual pathogens. You took a vaccine a long time ago for, let's say, chickenpox. It doesn't mean that you never have gotten the chickenpox again. What it means is that anytime a chickenpox virus particle has gotten into your bloodstream, your body has been able to fight it off easily, no problem, because it understands how to do it. So how does this happen? It happens involving two kinds of white blood cells, B lymphocytes and T lymphocytes. So here's how it happens. So let's say you get a little bacteria inside of your bloodstream here. The phagocyte will ingest that bacteria, and it displays that antigen on its outside surface. Once it displays this antigen, it actually goes over to the lymph nodes. And it kind of, I should say nodes, not notes. And what it does is it acts as like a warning signal. Remember, this is like the snitch cell. And it goes into your lymphocyte and is like, hey, the cell with this antigen is in our body, and we need to fight it off. So there is a kind of T cell called a helper T cell. And this helper T cell releases a bunch of those molecules that we talked about yesterday. Those molecules are called cytokines. And those cytokines activate a very specific B cell. They activate the specific B cell that knows how to fight off this particular antigen. Now, the antigen isn't the thing that it's fighting off, but it knows how to recognize that antigen. This B cell is the cell that makes antibodies. So what this B cell does is it divides a whole bunch of times into plasma cells. And these plasma cells are just antibody factories. And they just produce tons and tons and tons of antibodies. And these antibodies can float around and float around and float around your bloodstream. And every time an antibody encounters an antigen, that cell is destroyed. So antibodies are these really cool little proteins. They're a polypeptide, which means that they are made of 4 different actual protein structures, and they're kind of shaped like a Y. So we're going to draw a Y like this. These are 2 different shapes, like this. Each one of these lines represents a different part of the protein. So we have 1, 2, 3, 4 proteins that make up this one big protein structure. And this end right here is what we call the variable end, which means it can have all kinds of different little characteristics about it. And each individual antibody has a little bit of a different variable end shape that is specific for an antigen. So, for example, the chickenpox virus particle has a molecule on the outside of it that is called an antigen, and there is an antibody that has a very specific shape at the end of this here antibody that can attach to that antigen and destroy that chickenpox virus. Now, you don't always have chickenpox. You're not always exposed to it. So some of these lymphocytes, some of these B lymphocytes right here, will actually stick around in your body for the rest of your life. And they can be activated at any point in time to produce a bunch of antibodies to fight these things off. So within a day, you can see on this graph here, this system kicks in. Now, that's why you haven't gotten a lot of these diseases that you've had before, because your body is able to fight them off before you show any symptoms to them. So, speaking of fighting things off, let's talk about a kind of molecule that you can be prescribed to fight off an infection. And that molecule is called an antibiotic. Now, antibiotics are molecules, and they are able to block certain processes in prokaryotes. This is really important because bacteria are prokaryotes. They cannot fight things off from eukaryotes. And if you think back to the first day that we talked about immunity, you'll remember that there are some eukaryotes that are pathogens, like worms and protists and things like that, lice. And antibiotics cannot fight these things off because they only target molecular processes that happen in prokaryotes, not in eukaryotes. And for the same token, these things can't fight off viruses too. Viruses cause colds and flus and things like that. And there are some people that go to their doctor and demand an antibiotic to fight this cold or flu off. It won't help at all because colds and flus are caused by viruses, and viruses don't have metabolism, which means viruses don't have molecular processes that happen inside of them, and therefore these antibiotics cannot fight off viruses. So there's a few different ways that these molecules can work. Let's see, I've got a pretty good picture here. Definitely a pretty good picture. Here it is. Okay. All right. So this is a neat little image that explains how some of these antibiotics will fight things off. So, I'm sure you've heard of penicillin. Penicillin is what we call a beta-lactam antibiotic. You don't need to know that breakdown right there. But what you do need to know is that what penicillin does is it causes the prokaryote to not make a very good cell wall. There's other ones that do the same thing, cephalosporins, carbapenems, monobactams. I've never heard of those. Vancomycin and bacitracin I have heard of. And by not making that cell wall, these prokaryotes can break apart really easily inside of your bloodstream. Your bloodstream is kind of like white water rushing rapids, not a nice smooth flowing river. And when prokaryotes don't have that rigid cell wall around them, they tear up real easily. Nucleic acids, remember, are DNA and RNA. And there are different kinds of antibiotics. I've heard of sulfonamides and rifampin. I've never heard of these two, but they must exist because I found this picture on the internet, and the internet's always right. And these antibiotics will interfere with the DNA or the RNA inside of the cell so it can't reproduce. And remember that antibiotics harm you either by making and releasing tons of toxins or by reproducing and competing with your cells for nutrients and space. And so if they can't reproduce, well, your body could probably fight off one or two of them, but just not the millions that come when they reproduce. And then finally, protein synthesis. I've heard of tetracyclines, and none of these other ones I've heard of, but they attack the ribosomes inside of prokaryotes so that these prokaryotes can't make the proteins that they need to survive. So you've also heard, I'm sure, that there are prokaryotes that have evolved a type of antibiotic resistance. And they do this. Antibiotics become resistant in a variety of ways. Nope, I want to do this. There we go. Let's make this picture bigger. All right. Sometimes the microbe, the prokaryote, will you will come up with a way to make an enzyme that can inactivate the drug that you're taking. Sometimes the prokaryote will be able to make something that will grab on to that the target of the actual antibiotic, and if it grabs onto it, the antibiotic, I mean, it's just a molecule. It doesn't know how to behave. It's attracted to this thing, but unfortunately, this thing doesn't do anything, and so the prokaryote still stays alive. Some prokaryotes have evolved nice, thick, rigid cell walls, so that the drugs can't be taken up into the prokaryote. And this one's really neat. Some prokaryotes have even come up with proteins that sit in their cell membranes, and as soon as the drug comes in, this pump actively recognizes those things and pumps them out of the cell. That's really, really, really interesting. But prokaryotes aren't complex, weird, crazy, difficult thinking machines. They are just living things that behave like all other living things. And so let's take, let's draw ourselves a little population of prokaryotes. So here's going to be a little petri dish. We're going to draw like a bunch of blue prokaryotes and a bunch of green prokaryotes. We're going to draw them all the same shape here. A couple of red prokaryotes. Then we'll draw one black prokaryote. And let's say that these all represent the same species of prokaryote, but there's different varieties of this species, just like there's different varieties of us. There are darker-skinned usses and lighter-skinned usses. There's curly-haired and straight-haired usses, but we're all us. And the same is with these things. And let's say that this different characteristic we're representing by the color that we drew them. So we have the black prokaryotes, and we have the green prokaryotes, we have the red prokaryotes, and we have the blue prokaryotes. They're all the same kind of prokaryote. They just have slightly different characteristics from one another. Well, here's the thing. The environment that surrounds the prokaryote can change. If you're a prokaryote happily living in and infecting a body, and all of a sudden that body takes a particular drug, like an antibiotic that kills it, your environment has changed. And let's say that this particular antibiotic is able to kill all of these bacteria except for one kind. The blue ones all die. This antibiotic kills these blue ones. The red ones all die. The antibiotic kills those red ones, no problem. And the green ones all die. The antibiotic kills all those green ones. But for some reason, there's this little characteristic that made that black prokaryote a little different. And that black prokaryote is the only one that can survive. Now, in our new environment, we only have this black prokaryote. It has no more competition. It's not competing for food and resources or anything like that. And so this black prokaryote can divide into two, and this black prokaryote can divide into two, and this one can as well. What's happening to the population numbers of our prokaryotes here? It's increasing. And if this person tries to take this antibiotic again, it will not kill this prokaryote because it had antibiotic resistance. So antibiotic resistance is a real problem in today's world because we throw antibiotics in everything. Sometimes some of the clothes you wear are antibiotic. People take drugs all the time. Not drugs, I mean, I know what you're thinking of. People take drugs like penicillin, like too much, too often, too frequently, and they don't take the full course of them, and as a result, the things that survive may be resistant. Notice how I said may. It doesn't mean they are, it just means they may be resistant. Maybe they survive for a different reason. But this antibiotic resistance is a problem because then we can't use our antibiotics to fight things off. And so all of those parents that have gone to the doctors, doctor, we need something for my child. He has a cold. And the doctor says, no. We're not going to give you an antibiotic. It won't help. In fact, it'll kill off bacteria and leave behind ones that may have resistance to it. And now this penicillin won't help the kid at all. But the parent demands it, and some doctors give in. and they prescribe their kid an antibiotic, and now we foster this sort of resistance. Hand sanitizers used to be made with an antibiotic until we started to see bacteria that was resistant to it. The bacteria didn't choose to become resistant to it. It's just that different bacteria have different properties. And sometimes those properties are really helpful. All right. And we're going to talk about two more things here today. Let's talk about one specific antibiotic, and that is penicillin. Penicillin was discovered in one of my favorite stories, and one that a lot of you have probably heard of, by a guy named Alexander Fleming. Alexander Fleming was doing some experiments, and he had some petri dishes, and he was growing some bacteria in these petri dishes, and then he noticed that there was this spot where some mold was growing. And around the mold, there was zero bacteria growing. There was this whole area right around here where no bacteria would even come close to. And Alexander Fleming made that sound that scientists make when something really big is about to happen. And that sound that he made was, huh. So Alexander Fleming is really kind of like the picture-perfect, like, sort of scientific observer. He didn't just pick up that dish and say, oh, there's mold on this, and throw it away. He picked up that dish and said, oh, there's mold on this, but wait, why is there no bacteria growing around there? And Alexander Fleming said one of the greatest things that I think any person has ever said, and that is that in the case of chance... Nope, that is not the exact quote. I'm just going to write down my version of the quote here. Okay. And that version is that chance, so random chance, favors the prepared mind. You know, sometimes a lot of people will say, oh, he got lucky he discovered this, or he got lucky he made that, or he got lucky he was discovered by this person, or so on and so forth. And that's garbage. Totally disagree with that. Alexander Fleming didn't accidentally discover penicillin. Alexander Fleming had a trained scientific mind through years and years and years of research and study and interest in the world around him. And Alexander Fleming, in a very weird situation, noticed something, and then rather than throw it away, he thought, well, that's interesting. You know, there's a lot of stories about this. Bill Gates wasn't just a smart guy that, like, stumbled into creating Microsoft Windows. Like, I've read a book about Bill Gates, and he... in a time when computers were this really rare thing that nobody could access, Bill Gates was a high school kid who would go and wake up and walk to his university at 2 a.m, which was the only time he could get access to a computer to play. You know, the Beatles didn't just get a record contract because somebody saw them. They spent several years in Germany playing 2 or 3 shows a night in some club in a basement, perfecting and honing their abilities to, like, write music. Wu-Tang Clan is the same way. Walking through the streets of New York, just giving their tape to everybody, and always working together, and always freestyling, and always doing these things. And chance doesn't just happen. Chance favors the prepared mind, and that's the real attempt in science classes and in school, is to prepare your mind so that when something does happen, you are able to say, like, well, that's really important. So penicillin was discovered by Alexander Fleming, but there were 2 scientists that really worked out, like, its value. And these 2 scientists were Florey and Chain. So it turns out that this mold was making this molecule called penicillin. This mold was well known. It's a species of mold called penicillium, and it makes this molecule called penicillin. So Florey and Chain were like, I wonder if this could help us out. If it kills bacteria, maybe it'll help us out. So Florey and Chain literally injected 8 mice with a dangerous bacteria. 8 mice. 8, you guys. Just 8. That's going to be really important. 4 of them, they gave penicillin. 4 of them, no penicillin. All of the ones with penicillin survived. All of these died. And Florian Chain did something that nobody in the world of science would do today. And then they were like, that's good. We're done. Send it out. Now, they got real lucky that this worked. It just so happens that in 1940, when they did this, World War II was happening, and people were getting injured and dying of bacterial infections because of battleground injuries. And so Florian Chain started making penicillin and sending it out, and as a result saved thousands and thousands and thousands of lives in World War II. But this is not the case. There's a lot of medicines that have caused a lot of problems, even after doing some research on them. And so this was sort of the start of this wonder drug sort of industry. And so since the start of this industry, a lot of rules and regulations and laws have come around. So finally, let's talk about our last little bit today, and that is something that penicillin can't kill. If penicillin can only block molecular processes in prokaryotes, it can't kill things in viruses. And let's go back to these T cells, and let's talk about a virus that is so dangerous that it wipes out your ability to have immunity. And that virus is HIV, or the human immunodeficiency virus. HIV specifically targets those helper T cells. Now remember that the helper T cells, they release the cytokines that activate the B cells, and the B cells make the antibodies. And so what HIV does is it gets inside of the T cells and it hijacks the DNA in the T cells with its own. And so these helper T cells then just become factories to make HIV particles over and over and over again. So instead of helper T cells doing the things that they're supposed to do to help out your immune system, they just become HIV factories. And this process of helping out your immune system is gone. And that leads you to get a disorder that can cause you to die from real simple diseases that you might not have died from, and that is AIDS. AIDS stands for Acquired Immunodeficiency Syndrome, because your immune system is deficient. Okay. So how this is just a real dangerous process. HIV, is transferred through the exchange of bodily fluids. It has to be body fluids exchanging. And there are people that say all kinds of things like, oh my God, don't drink out of the same water fountain as somebody, and oh my God, don't do this, don't sit on the same toilet as somebody, and so on and so forth. You're not exchanging bodily fluids in those processes, and so those are not dangerous things. Specific cases of bodily fluids, obviously, are any kind of sexual contact. You reduce your risk by taking certain precautions, like wearing condoms and things like that, but doesn't mean that it's a zero. Intravenous drug use, when people share needles. When people share needles with like heroin and things like that, there's a chance that you could transmit HIV that way. There's cases like early on where, before they really knew about HIV, where they would be giving HIV-infected blood to people who otherwise weren't, were totally healthy and not at any other risk. The first cases of HIV appeared in the homosexual male scene in California, so there's lots of unprotected sex happening there. And then throughout the mid-'80s, it got to be to the point where it came into heterosexual people as well and started spreading out further from there. But also HIV can be passed on from a pregnant mother to her children. because of breastfeeding. Also, during childbirth, you know that there's blood associated with that, and so as a result, HIV could be transferred that way as well. Okay, that's it for today. Tomorrow you will get your immune assignment, and that'll be it. All right, take it easy.